Hi my TechSci fam, welcome back to another series on this channel. I want to big up all my subscribers, all the persons who've been leaving comments, been liking my videos, and been sharing it with persons you know the video could really help. So in this series, we're looking at the graphical resolution of forces. So if you're doing physics or BMed or any other related subject that has this topic, this is the series for you. In this one, I'm looking at the basics where I talk about what a force is as well as a vector line. So come with me and we'll explore this content. Okay, so as we get into this video, the first thing I want to highlight is what exactly we mean by a graphical resolution or graphical method. It basically means that we'll be using diagrams to find the resultant of forces rather than using calculations, which is another method that we can also use. So let's get into it. So the first question I'd ask, why find the resultant of forces in the first place? Now, when we're dealing with structural systems, it's very often necessary that we need to find the sum of forces that are acting in a system so that we can ensure that our design is safe and it's sound and it will be free from later damage or later destruction due to improper loading. So we can look at resultant to say it's the sum of two or more forces. That's one of the basic ways of defining the resultant. Then finally, the resultant of concurrent and non-concurrent coplanar forces can be done graphically, and that's either using a triangle, a parallelogram, or a polygon of forces. And that's what we're going to explore. So you have your triangle method, your parallelogram method, and then your polygon. Now, please note the polygon, the triangle, and the parallelogram may not necessarily look like these. It's dependent on the forces that are acting in the system. Note, many times in questions, you will see the value for the force being a ton. So just to give you an equated value, 1 ton ideally is 9.964 kilonewtons. The value continues beyond the 4, but I rounded it to 3 decimal places. But when we're dealing with calculations, to make it a little easier, we round it and say 1 ton is equal to 10 kilonewtons. So using this knowledge now, you are able to make relation between what you see on the diagrams and a ton. So sometimes you'll see kilonewtons, sometimes you'll see ton, but now you understand the relation between the two. So now let's look at going from a force line to a vector line and then to a vector drawing. So let's look at force lines first. A force acting on an object or system has magnitude, direction, and line or point of application. Now I'll pause here to say check the iCards. If you missed my first video where I looked at concurrent, coplanar, parallel, and all the types of forces that we can come across, or some of the forces that we can come across, then you can check the iCard for that video. Continuing, forces are represented by an arrow. They must have an arrow. And why is that? Because a force must have a direction. So that's why an arrow is necessary. The magnitude can be indicated by a label, meaning you indicate the value of the force, or you could use scale drawing, ensuring that the length of the arrow is equivalent to the force itself. And like I said, scale drawing. The direction of the force is represented by the angle of the force line. And so that's that. And finally, force lines are identified by capital letters, and this just makes it easier rather than having to be calling force 1, force 2, force 3, force 4. You might hear a force being referred to as A, AB, or so on and so forth. So now let's look at a little depiction. So there you have a contact surface. Can represent anything, can be a table, can be whatever you want. It's just a contact surface. And then now here you're seeing an arrow, and the force, in this case, it's less than a kilonewton. It's 20 newtons that is being applied to this surface. So in this case, we call this force AB. Now let's look at vector line and vector drawings. Forces acting on a system, we can use vector lines to represent them. And why we can do this, remember that a force is a vector. So it's pretty much ideal then for us to say that we can use a vector line to represent it. The length of the vector line is drawn to a scale to represent the magnitude of a force. Now, unlike when we're looking at force lines where we're saying that you can just label the force line as is in this example where I've placed 20 newtons, when you're dealing with vector lines, you have to ensure that the length of the vector line is to scale and it represents the magnitude of whichever force it is representing. The angle of the vector line should be equal to the line of action of the force. So basically, whatever angle you draw your vector line to, it should be equal to the direction the force is acting. An arrowhead on vector lines indicates the sense of the force, meaning whether the force is pushing or pulling. Remember, that is the basic definition of a force. It either pushes or pulls a system or an object. Vector lines are labeled with common letters in the same order as the force they represent. So, this is key. You have to recall that force lines are identified by capital letters, but vector lines are labeled with common letters. Very important. And it should be the same. So in this case where we have force AB, when we are representing it as a vector line, it should also be AB in the same order. Arranging the vector lines for the forces in a system, we get a vector drawing. Makes sense, right? Pretty cool. So as long as you are arranging the vector lines for the forces that are acting in a system, you will get a vector drawing. Or sometimes you'll hear it being called a vector polygon. Same thing. Vector drawings can be in the shape of a triangle, a parallelogram, or a polygon. So now I'm going to demonstrate. So in this example, you see me place 3 notches. That's just to indicate 1 unit each. So the vector line now is drawn, and based on what we're seeing, this would be 1 unit, this would be 1 unit. So the total length of this line is 2 units, whether the unit was centimeter or millimeter. So this would represent 2 units. So naturally, remember, we must label it with common letters, just as you've seen here, in the same order as the force they represent. So this is representing this, and so the label must be AB in the same order. Now finally, we need to indicate what scale we used to draw this vector line. And that is key. You have to indicate the scale. So if this force was 20 newtons, and this vector line was drawn to 2 units, what then do you think would be a suitable scale? If you guessed 1 unit to 10 newtons, then you would have been correct. So much so that from this point to this point would represent 10 newtons, and then from here to here would represent another 10 newtons. So that would be 10 plus 10 to give you 20. So remember, it is absolutely important that you represent your scales. So now, I hope you would have gotten what we've covered so far. We're now going to 2 simple questions where we are required to represent a force using a vector line. So the instruction says use a vector line to represent the force in the diagrams below. So in A here, we are seeing this is representing a fixed area. It could have been a ceiling, could have been attached to a beam, could have been whatever it's attached to, even a tree. So that's what this is representing, that the weight here, this 20 kilonewton weight, is affixed to some fixed point, or is attached to some fixed point. Now, you see this load now, and it can be called a weight, it can be called a load, 20 kilonewtons, and this is applied to the string here. So, let me just get my pen. This weight on the string is pulling downwards. So this force is pulling downwards. Therefore, when we are representing this, we will represent this vector line in this direction, and we remember we must represent it to scale. We also have this one over here, where you see 1 force, and it is 30 degrees to the horizontal, and the magnitude of it is 15 kilonewtons. So we're now going to jump over to AutoCAD and represent this. Key thing I want to point out before we go, once you have a weight attached to a string or whatever it is pulling downwards. A setup like this, the weight is always pulling downwards. If you think of you holding an object on a string, you would recognize that you're feeling a pull from where you are holding it. And so that's why whenever we have forces attached in this manner, we would show the arrow for the force acting downwards, because that is where the force is acting. And of course, that has to do with the pull of gravity as well. So that's why we would represent the force in that way. So let's go over to AutoCAD. Okay, so I've pasted the question in AutoCAD, and now we're going to get right into representing these forces as a vector line. So we're going to start with this one. So we have 20 kilonewtons, and I'm going to get line, and I'm going to use a scale of 1 to 1. So I'm going to draw the line 20. So now I'm going to be drawing on my arrowhead. So I'm going to do polyline, P-L-I-N-E, as my command. And I don't necessarily have to put my arrowhead at the end here. And when you're doing that, you have to be careful, because if you put the arrowhead here and then extend it further, you know that your line would be greater than the length it's supposed to be. So you have to be careful with that. So after polyline, I choose half width. Could have done H enter as well. Since this is 20, I'm going to make it 1, enter, 0, enter. Let's see how big it is. Okay, that's fine. And that's my arrowhead. That's as simple as how I drew the arrowhead. So if I did it at the end, all I'd have to do now is just to move it to the end of the line so that my entire vector line is the length it's supposed to be. So let me just dimension to make sure. 20, beautiful. So that is that. So what I'm going to do, because this question was A, I'm going to name this force A. And then this one is B, I'll name this force B as well. So this force, I'm going to be naming it A. So let's type T-E-X-T. Could have named it AB, and my height will be 2, rotation 0. Remember, it's a common letter because this is a vector line. And then I indicate my scale. And I said 1 millimeter. I can put a colon or the word 2, 1 kilonewton. And that would be my scale for this one. Now, how would persons know that this line is actually to the correct length? I would dimension it. So I would go from the top to the end, and there you would have, I could even move this closer in the middle here, and there you would have this vector line representing this force at a scale of 1 millimeter to 1 kilonewton. So now let's look at our second example. And this one is not vertical as A, but it's at an angle of 30 degrees. And it can be done just the same way. So again, I need to determine what scale I'll use. And I think I'm going to use 1 millimeter to 1 kilonewton again. So I specify my start point. And then now I need to go to an angle. There are more than one ways we could get this angle. We could have used polar and set to 30. It's already set to 30, so that's one way. So polar set to 30, and then you would recognize that you're getting what we call tracking, a tracking line at 30 degrees. And so then I could type in my 15, or I could have done the less than sign, which represents angle, and then type in the desired angle, seeing it here on screen right here, then press enter. And then I would get a line that is restricted to 30 degrees. Then now I type my length, 15, because I'm using a scale of 1 millimeter to 1 kilonewton. And that would be that. I'm again going to put on my arrowhead. Okay, so I tried 2 and I realized it's big, so I'm going to go again, H enter, and let's make it 1 this time, 0 enter. Looks better, so we can work with that and keep it at 2. Always remember to move it so that your line is not longer than it should be, because that can cause some serious problems. So now I'm also going to be putting a little line here so that I can measure. And I'm going to be dimensioning. So I'm going to use a line this time because it's at an angle. So there you have the 15. Then I'm going to use angular to get my angle between here and here. There's the 30 degrees. Now, because of the scale of my drawing, this 30 degrees is a little bit big. So I'm just going to reduce the size. And now remember, I'm going to label my force. And there you have 2 diagrams where I'm representing the forces from these diagrams as a vector line, ensuring that it is correct in magnitude, which in this case is 20, in this one is 15, and in direction. In this one, it is a vertical line, or we would say 90 degrees. In this one, it is at 30 degrees. And of course, we have to remember to always represent our scale. Alright, so I hope the video was helpful. I hope you have learned so much about forces and vector lines or vector drawings so that you are equipped to advance as we go through this series. So, as usual, remember to like, share, and subscribe so that other persons can benefit from the content of this video. Thank you for joining. Catch you in the next one.